In this video, we're going to solve these 5 problems here that are related to the binomial theorem. So the first 2 problems involve expanding brackets, and we can use Pascal's triangle to help us with that. Question 3, this identity here is known as Pascal's rule, and we're going to prove that, and then we're going to use that in question 4 to help us prove the binomial theorem. And then question 5, we're going to make use of the binomial theorem to prove this inequality here. Okay, so let's get started solving these problems. Question 1. We're going to expand x plus 3, all raised to the power of 4, and we can use Pascal's triangle to help us. So in this red box over here, we've got the first 4 rows of Pascal's triangle written out, and they will give us the coefficients that we need. So by convention, we call this top row, row 0, and that is because we want our row numbers to match up with the indice here. So if we look at row 4, that is going to be this row here. So our coefficients that we need are 1, 4, 6, 4, 1. So expanding this out then, so we're going to get, for the first term, our coefficient is 1. So we're going to get 1 times x to the power of 4. Because we're thinking of choosing none of the 3's, so we have to choose all of the x's, and our coefficient for that is 1. The next term, our coefficient is 4, so we're going to have 4 times x cubed times 3. So we're just choosing one of the 3's, so we could also think of that as 3 to the power of 1. And then the next term, our coefficient is 6, so we're going to have 6x squared times 3 squared. And then we've got our coefficient is 4, so we're going to have 4 times x times 3 to the power of 3. And then our final term, coefficient is 1, and it's going to be 3 to the power of 4. So 1 times 3 to the power of 4 is just 3 to the power of 4. And then we can simplify this out. So our first term is just x to the 4, and then plus, well, 4 times 3 is 12, so we're going to get 12 x cubed, and then plus, well, 3 squared is 9, so 9 times 6 is 54, so we have 54x squared, and then 3 cubed is 27, and 27 times 4 is 108, so we're going to get plus 108x, and then 3 to the 4 is 81, so plus 81. So that is question 1. Question 2, we're going to expand x squared plus 2 over x all raised to the power of 5. So to get the coefficients we're going to need in our expansion, we're going to have to look at the 5th row of Pascal's triangle. So in this red box here, we've already written out the first 4 rows of Pascal's triangle. So we'll write out the 5th row now. So we're going to get then 1, 5, 10, 10, 5 and 1. So they are the coefficients. So expanding this out then, for our first term, we're going to have our coefficient, which is 1 times x squared raised to the power of 5. So we're thinking of it as choosing none of the 2 over x terms. So that means all 5 of our terms must be that x squared term. So that's why we've got that raised to the power of 5. Then the second term, got our coefficient, which is 5, and this time we're going to think of it as choosing just one of the 2 over x terms, so that means the remaining 4 terms must be that x squared. So we're going to have x squared raised to the power of 4 times 2 over x, and we've just got one of those terms, so we can think of it as just raising it to the power of 1. So for each successive term, we're just going to take off 1 from the power of the x squared term, and we're going to add 1 on to the power of this 2 over x term. So that means for our third term, we're going to have our coefficient, which is 10, and that's going to be multiplied by x squared to the power of 3 times 2 over x to the power of 2, and carrying on, our next coefficient is also 10, so we're going to have 10 times x squared to the power of 2 times 2 over x to the power of 3. And the next term, coefficient is 5. So it's going to be 5 times x squared, and this is just to the power of 1, times 2 over x to the power of 4. And then the final term, well, our coefficient is 1. We're going to have none of the x squared terms, so we're going to have 2 over x to the power of 5. So we'll simplify and tidy this up a little bit now. So you could just do it all in one step if you're comfortable with that, but I'm just going to write it out in 2 steps here, just so we're clear exactly what is going on. Okay, so the next line then, well, x squared all to the power of 5 is x to the power of 10. Then our next term, so we're going to have 5 times 2 is 10, and then it's going to be x to the power of 8 over x, and then plus, well, 2 over x all squared is 4 over x squared, so we're going to have 10 times 4 is 40, and it's going to be x to the power of 6 over x squared. And then the next term, so all 2 over x all cubed, so it's going to be 8 over x cubed, so 10 times 8 is 80, and then it's going to be x to the power of 4 over x cubed. And then the next term, so 2 over x all to the power of 4, so that's going to be 16 over x to the power of 4, and 16 times 5 is 80, and then it's going to be x squared over x to the power of 4, and then our last term, 2 over x all to the power of 5, is going to be 32 over x to the power of 5. And just simplifying this, then we're going to get x to the power of 10 plus 10 times x to the power of 7 plus 40 times x to the power of 4 plus 80 times x plus 80 over x squared plus 32 over x to the power of 5. Okay, and that is our final answer then. So that is question 2. Question 3, we're going to prove Pascal's rule, which is given by this identity here. This n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So to help us prove this, we're going to use this fact here, that n choose k is equal to n factorial over k factorial times n minus k factorial. So if we look at the right hand side of the equation, well then we're going to get n minus 1 choose k minus 1 plus n minus 1 choose k, that's going to be equal to n minus 1 factorial over k minus 1 factorial times n minus 1 minus, and don't forget the brackets, k minus 1 factorial plus n minus 1 factorial over k factorial times n minus 1 minus k factorial. So now we'll go about trying to simplify this and to write it over a common denominator. So if we look at this term here, in the denominator we've got this k minus 1 factorial. So if we times the numerator and denominator through by k, well then in the denominator we're going to get k times k minus 1 factorial, which is just equal to k factorial. And we see that in this term here, we've got k factorial in the denominator. So we'll do that, and then we'll try and simplify it a bit more. So we get then that this is equal to k times n minus 1 factorial, and that is all over k times k minus 1 factorial times n minus 1. And just getting rid of those brackets, it's going to be minus k, and then minus 1 is plus 1 factorial. So we won't simplify this term just yet. We'll write out the next term, and then we'll try and find a common denominator. So then we get plus n minus 1 factorial, and that is over k factorial times n minus 1 minus k factorial. So now let's look at the denominators of these two terms that we've got here and see what we've got in common so far. So we've got this k factorial here, and then over here we've got this k times k minus 1 factorial, which is equal to k factorial. So we've got those terms in common. And then if we look here, we've got n minus 1 minus k factorial, and then this part here is n minus 1 minus k plus 1 factorial. So we can write this out as n minus 1 minus k plus 1 times n minus 1 minus k factorial, and then we'll have this term here in common. So let's do that first. So looking at this term here then, well, that's going to be equal to k times n minus 1 factorial, and that's going to be all over k factorial times n minus 1 minus k plus 1 times n minus 1 minus k factorial. And then our next term is going to be plus n minus 1 factorial all over k factorial times n minus 1 minus k factorial. So now if we look at this term here, if we times the numerator and denominator by this n minus 1 minus k plus 1, well, then we're going to have a common denominator for those two terms. So we'll do that. So timesing the numerator by n minus 1 minus k plus 1, and the denominator n minus 1 minus k plus 1. Okay, so now we're going to write these out over our common denominator. So it's going to be equal to k times n minus 1 factorial plus n minus 1 factorial times n minus 1 minus k plus 1, and that is all over k factorial times n minus 1 minus k plus 1 times n minus 1 minus k factorial. So we're almost there. So we can just simplify this a bit more then. So we can see in the numerator we've got this common factor of n minus 1 factorial, and we can go about simplifying our denominator a bit more as well. So we get then that this is equal to n minus 1 factorial times k plus n minus 1 minus k plus 1, and that's going to be all over k factorial. And then for this term here, this n minus 1 minus k plus 1, we can cancel out the minus 1 and plus 1, so we're going to be left with just n minus k, so times n minus k. And then for our next term, I'm going to write it out as n minus k minus 1 factorial, just to make it clear what is going on, because n minus k times n minus k minus 1 factorial is just n minus k factorial, so we can simplify that denominator a bit more. And our numerator, well, we're going to have this k and then minus k, so they cancel, and then our minus 1 and plus 1 are going to cancel. So we'll write out what we've got then. So in our numerator, we're going to have n minus 1 factorial times n, and that's going to be over k factorial times n minus k factorial. And now in our numerator, we've got this n minus 1 factorial times n, so that is just equal to n factorial. So we're going to get n factorial in our numerator, and then we've got our k factorial times n minus k factorial. In this expression here, Well, that's just our definition of n choose k. So this then is equal to n choose k as required. So that completes our proof of Pascal's rule, and that finishes off question 3. Question 4. We're going to use mathematical induction to prove the binomial theorem, which is given by this equation here, and just for convenience we will refer to it as equation 1. And it's valid for all integers n such that n is greater than or equal to 0. So just to keep our notation simple, we'll let P of n represent equation 1. And the first thing we want to do when proving something by induction is we need to prove it's true for the base case. So as we're trying to show that this equation holds for all integers n greater than or equal to 0, we need to prove that equation 1 is valid for when n is equal to 0. So what we have to do then is just plug n equals 0 into our equation and make sure the equation holds. So for our base case then, we have n is equal to 0, and then the left hand side of the equation, that's just going to be x plus y to the power of 0. It's going to equal, the right hand side we're just summing from k equals 0 to 0, so we're going to just get one term, so that n choose k just becomes 0 choose 0, and then the other terms we're going to just have x to the power of 0 times y to the power of 0, which is just equal to 1. So this implies then, well, that left hand side is just going to equal 1, and 0 choose 0 is also equal to 1, so we have 1 equals 1, so therefore the left hand side equals the right hand side, so we can say that P of n is true for when n equals 0. So we have proved that the base case is true. So now we make our hypothesis statement, that is, we assume then that P of n minus 1 is true. So that just means we assume that the equation holds when n is replaced by n minus 1. So what we need to show then is that if P of n minus 1 is true, then so is P of n. So we have then x plus y to the power of n is going to equal x plus y times x plus y to the power of n minus 1, and that is going to equal x plus y times the sum going from k equals 0 to n minus 1, then we have n minus 1 choose k times x to the power of n minus 1 minus k times y to the k. So we know that those parts in blue there are equal by our hypothesis statement. So now we'll just expand out the bracket. So we'll have x times this term here plus y times this term here. So we get then, multiplying the term by x first, we're going to have the sum going from k equals 0 to n minus 1. N minus 1 choose k times, we'll just add 1 to the power of x, so it's going to be x to the power of n minus k times y to the k, plus we'll just multiply the term by y, so we're going to get the sum going from k equals 0 to n minus 1. We have n minus 1 choose k times x to the power of n minus 1 minus k times y to the k plus 1. So now we want to aim to try and write all this out under one summation symbol. So we're going to need to make sure the indices for our x terms are the same and the indices for our y terms are the same. So to do that, well, if we look at this term here, if we replace k by k minus 1, well, then we're going to get y to the power of k minus 1 plus 1, which is just y to the power of k, and our x to the power of n minus 1 minus brackets k minus 1, well, that's going to simplify down to x to the power of n minus k. But if we replace k by k minus 1, then we're going to have to replace our summation indices. So instead of going from k equals 0 up to k equals n minus 1, we're going to sum from k equals 1 up to k equals n. So we can see that these terms here are just exactly the same. So for example, if we plug k equals 1 into this n minus 1 choose k minus 1 part here, that would be our first term, and we'd get n minus 1 choose 0. And if we look up in the top one here, plugging in k equals 0, we also get n minus 1 choose 0. Then our final term, or for the bottom part, we'll plug in k equals n. So this part here again, well, that's going to be n minus 1 choose n minus 1, and then plugging in n minus 1 in the top term for k, for the final term, well, it's also going to be n minus 1 choose n minus 1. And you can check that it's going to work out for the indices as well of x and y. Okay, so we'll just write this out again, and we'll simplify these indices here. So we can almost write this out under one summation symbol, because we've got these terms in common now. But our problem is the indices of summation. So this one here on the left is going from k equals 0 to n minus 1, and this one is going from k equals 1 up to k equals n. So if we can make those indices the same, then we'll be able to write all this out under one summation symbol. So looking at this left term here, well, if we write out the first term, which is when k equals 0, and then add that to the summation from k equals 1 up to k equals n minus 1, of all that stuff in there, then we're going to get, for our first term, k equals 0, n minus 1 choose 0, which is just 1, times x to the power of n times y to the power of 0. So we're left with just x to the power of n. So what we get then is that left term is going to be equal to x to the power of n plus the sum going from k equals 1 to n minus 1. And then we have n minus 1 choose k times x to the n minus k times y to the k. So now we've got this starting from k equals 1, and it finishes at k is equal to n minus 1. Then our second term here, well, we're finishing on k equals n. So if we write out that term where k is equal to n, well, we're going to get n minus 1 choose n minus 1, which is just 1, and then x to the power of 0, which is just 1, and then times y to the power of n. So we're left with just y to the power of n. So writing out that second term then, well, we're going to get plus our summation going from k equals 1 to n minus 1, because we're writing out that term when k equals n. We'll do that at the end. Then we have n minus 1 choose k minus 1 times x to the n minus k times y to the k, and then outside our summation sign we're going to have plus y to the power of n. So now looking at our summation terms, we're going from k equals 1 to k equals n minus 1 in both cases. We can also note we've now got this term in common here, this x to the n minus k times y to the k. So we're going to write all this part out here under one summation symbol. So what we're going to get then is this is equal to x to the power of n plus our sum going from k is equal to 1 up to n minus 1. And then we have our n minus 1 choose k plus n minus 1 choose k minus 1, and that is multiplied by our x to the n minus k times y to the k. Then outside our summation we have our y to the n, so plus y to the n. Okay, so simplifying this a bit more then, this is going to be equal to x to the power of n plus our sum going from k equals 1 to n minus 1, and then we have n choose k times x to the n minus k times y to the k plus y to the power of n. Okay, so that part in red there, that is just making use of Pascal's rule. So this term here, that's almost the same as our right hand side of equation 1, except here we're summing from k equals 1 up to k equals n minus 1. But we can note that when we had k equal to 0, or we got our x to the n term, And when we had k equal to n, well, that's when we had our y to the n term. So we can put those x to the n and y to the n terms inside our summation symbol, and then we'll be summing from k equals 0 up to k equals n. So we'll write that out. So this is equal to our sum going from k equals 0 to k equals n. Then we have our n choose k times x to the n minus k times y to the k, and that is equal to the right hand side of equation 1 as required. Okay, so we've shown then that if p of n minus 1 is true, then so is p of n, and as we have proved the base case for when n equals 0, p of n is therefore true by mathematical induction for all integers n such that n is greater than or equal to 0. So we'll note that down. So we have now finished our proof of the binomial theorem, and that concludes question 4. Question 5. We're going to use the binomial theorem to show that 1 plus 1 over n, all raised to the power of n, is less than 3 for all n greater than or equal to 1, where n is an integer. So you might recognize this part here, that if we were to take the limit as n goes to infinity, then we just get the number e. So basically here what we're trying to show is that 3 is an upper bound for that term on the left hand side, regardless of how large we take n. So from the binomial theorem then, we get 1 plus 1 over n to the power of n is equal to the sum from k equals 0 to n choose k times 1 to the power of n minus k times 1 over n to the power of k. Now 1 to the power of anything is just 1, so we can just write this out as the sum from k equals 0 to n choose k times 1 over n to the power of k. So because we know that n is greater than or equal to 1, we can write out the first term of our summation when k is equal to 0, and then take our summation going from k equals 1 up to k equals n. So we have then, for k equals 0, we're going to get n choose 0 times 1 over n to the power of 0, plus our summation going from k equals 1 up to n. Then we have our n choose k times 1 over n to the power of k. So this equals then, well, n choose 0 times 1 over n to the power of 0 is just 1 times 1, so that equals 1, plus, and then n choose k, we'll write out the definition of that. So that's going to be then our sum going from k equals 1 up to n. Then we have n factorial over k factorial times n minus k factorial times 1 over n to the power of k. So now we're going to rewrite this n factorial part as n times n minus 1 times n minus 2 all the way up to n minus k factorial. So we're going to have then, this is equal to 1 plus our sum from k equals 1 up to n, and then in the numerator we're going to write that n factorial as n times n minus 1 times n minus 2, and it's going to go up to, well, the term before n minus k is going to be n minus k minus 1, and then we'll multiply that by n minus k factorial. So this part that I've just written out, that is exactly the same as n factorial, and that is going to be all over k factorial times n minus k factorial, and we multiply this whole term by our 1 over n all to the power of k. So these n minus k factorial terms are going to cancel out, and then we're going to be left with just k factorial in the denominator. So we can write this out then as being equal to 1 plus a sum from k equals 1 to n, we're going to have 1 over k factorial times our n times n minus 1 times n minus 2 all the way up to our n minus k minus 1 term, and then that's all going to be multiplied by our 1 over n to the power of k. So we're going to look at this part here, this n times n minus 1 times n minus 2 all the way up to n minus k minus 1, that is multiplied by 1 over n all to the power of k. So if we think of this first n as, say, n minus 0, and then n minus 1, n minus 2, all the way up to n minus k minus 1, well, we've got k terms there, and then that 1 over n to the power of k, well, that has k terms in it, if we multiply it all out together. So we can think of that part then as, and I'll just write it up in the top right hand side in red here, as n times 1 over n times n minus 1 times 1 over n, etc., all the way up to n minus k minus 1 times 1 over n. So that means we're going to get then, well, n times 1 over n is just 1, and then n minus 1 times 1 over n is 1 minus 1 over n. So we'll write that out then. So what we're going to have is this is equal to 1 plus our sum from k equals 1 to n. We have our 1 over k factorial, and then we're going to have, well, n times 1 over n is 1, and then n minus 1 times 1 over n, that's just 1 minus 1 over n, and then our n minus 2 times 1 over n is 1 minus 2 over n, and we're going to keep going, and then our final term, well, it's going to be 1 minus k minus 1 over n. And that is going to be less than or equal to 1 plus the sum from k equals 1 to n, and we're just going to have 1 over k factorial. So to see why this inequality is true, let's first take n is equal to 1. So for n equal to 1, we're going to just be summing one term. That's when k is equal to 1. So if we were to plug that in into here, well, if k is equal to 1, then that part, k minus 1, is going to be 1 minus 1, which is just 0. And then the n is 1, so 0 divided by 1 is just 0. So we're left with just 1. And that's going to be multiplied by our 1 over k factorial. So the last two lines would then be equal. But if we take a bigger number for n, let's say n is equal to 3, so we're going to be summing from k equals 1, k equals 2, and k equals 3. So for k equals 3 then, well, this part here, this whole term, we're going to have 1 times, or 1 minus 1 over 3. And then our final term, our k minus 1, so if k is equal to 3, 3 minus 1 is 2, so we're going to be multiplying by 1 minus 2 over 3. And that 1 minus 1 over 3 and 1 minus 2 over 3, well, they're going to be less than 1. So what we're going to end up then is multiplying our 1 over k factorial by some number that is going to be less than 1, and therefore that is going to be smaller than just 1 over k factorial. So 1 over k factorial is always positive from k equals 1 up to n. So that means then this is going to be less than 1 plus the sum from k equals 1 to infinity of 1 over k factorial. So this next step is a little bit trickier to see. So let's just write out k factorial is equal to 1 times 2 times 3 up to k minus 1 times k. And that is actually going to be greater than or equal to 2 to the power of k minus 1. So let's just see why this is true. So if we take small values of k, say for k equals 1, well then the left hand side is just going to be 1, and the right hand side of that inequality is going to be 2 to the power of 1 minus 1, which is 2 to the power of 0, and that is just equal to 1. So they're going to be equal. If we pick k as 2, well then the left hand side is going to be 2 times 1, which is equal to 2, and the right hand side is just going to be 2 to the power of 2 minus 1, which is 2 to the power of 1, which is equal to 2. So if k is equal to 1 or k is equal to 2, then the left and right hand sides of this inequality are going to be equal. But as we take k greater than 2, it becomes clearer what is going on. So for example, if k is equal to 3, in the left hand side we're going to have 3 times 2 times 1, and our right hand side is going to be 2 to the power of 3 minus 1, which is 2 to the power of 2, which is 2 times 2. So our 3 times 2 is going to be greater than 2 times 2. And if k is equal to 4, well then we get 4 times 3 times 2 times 1 on the left hand side, and the right hand side going to be 2 to the power of 4 minus 1, which is 2 to the power of 3, so that is 2 times 2 times 2. And we can see then our 4 times 3 times 2 times 1 is going to be greater than 2 times 2 times 2. So in general then, the right hand side is just going to be 2 times itself k minus 1 times, and on the left hand side, well if k is greater than 2, we're going to have at least k minus 1 terms with at least one of them greater than 2, and our kth term is just going to be 1. So therefore k factorial is going to be greater than or equal to 2 to the power of k minus 1. So that is useful because what we know then is if we have 1 over k factorial, well that's going to be less than or equal to 1 over 2 to the power of k minus 1. So what we get then, if we look at this term here, we can say that is less than or equal to 1 plus the sum from k equals 1 to infinity, and we have 1 over 2 to the power of k minus 1. So looking at this term here, we can see that's an infinite geometric series with common ratio 1 over 2. And we know for an infinite geometric series, if the absolute value of the common ratio is less than 1, then we can find its sum. So for our one here, the absolute value of our common ratio is the absolute value of a half, and that is definitely less than 1. So we can find the sum then of this infinite geometric series, and we know the sum to infinity is equal to a, where a is the first term in our series, over 1 minus r, where r is our common ratio. So to find a then, we just plug k equals 1 to get our first term. So plugging k equals 1 into our summation there, we get 1 over 2 to the power of 1 minus 1, which is 2 to the power of 0, which is equal to 1. So we just get 1 over 1, and that is 1. And that's going to be over 1 minus, well, r is 1 over 2, so 1 minus 1 over 2. So we'll put this here, we'll substitute that into this term here. So what we're going to get then is this is all going to be equal to 1 plus 1 over 1 minus a half. So that's going to be equal to 1 plus 1 over a half, which equals 1 plus 2, which is equal to 3. So now we can just follow everything through. We've got our 1 plus 1 over n to the power of n was less than this term here, which was less than or equal to this term, which was equal to 3. So therefore then, we can say that 1 plus 1 over n all to the power of n is less than 3 as required. And that finishes off our final question.